All right. So the next kind of one is enthalpy of a reaction. So if you're given a reaction and you've done stoichiometry before, that's earlier in the chapter. So in enthalpy, what we're really looking at is looking at the heat. So if we're given the enthalpy value, it's going to scale that amount of heat per reaction. So if we just scroll on down, it's the difference between enthalpy and internal energy. Then at the heart of it, what we're looking at is, first of all, if the reaction is exothermic or endothermic. So if it's negative, it's exothermic. That means that during the course of the reaction, it's starting at a higher energy and it's going to fall down. So it's going to give off heat. And if it's endothermic, then that means it's going to take in heat and get cooler. And from the previous type of calculations, you're able to solve for that delta T. So um, the idea then is that we can treat heat as a reactant or product. And instead of writing it, the way we write it then is this. And so we have a balanced equation, and then we have this term here, delta H of a reaction is equal to that. And it's kilojoules per mole, and it's moles of reaction. And so in each reaction, we need two aluminum and one iron oxide to do it. So what we can do then is we can scale it then to either one of them, right? We can look at if we can look at either the metal or the oxide and do the same thing. So that's all this is to be able to do the same old stoichiometry we did with moles. Like if given moles of 2 moles of aluminum, then you would predict it would have this amount of heat. If you had 1 mole aluminum, it'd be half that amount. That's what it shows here. And or we can look at the iron oxide or anything. And so we can do moles and then grams, just standard stoichiometry for it. All right. Unfortunately, it has a terrible kind of example here. I don't like this one and don't have the time to build one up for you right now. So that's why I'm stopping here.